So welcome back. Uh, we are now going to look at the linear systems. But before that, want to say a word or two about higher order equations. Suppose you have a higher order equation. Suppose it's something like this. Nth derivative is given by f of x derivative some region of R of the xt plane, xt. Suppose this is a nth order, this is a prototype of the nth order differential equation where f is a function of the dependent variable x, its derivatives up to the order n minus 1 and t, and xn is given by the nth derivative is given by this. So I have put this one, this stands for di by dt to the power I of x is designated by x to the power I. That's the notation. Now, how do we handle this kind of equations? We have already done enough on first order systems. So what do? We show that this can be converted into a first order system. And then, the two systems are equivalent, or this equation is equivalent to a first order system. And therefore, the solution can be easily found. I mean, whatever theory you have developed for a first order system applies equally well for the higher order equations. For that, what you do is you introduce the following variables. Define x. Then you define x2 as x derivative, which is equal to x1 derivative. So, and so on, xn to be n minus 1 derivative, which is equal to x1 to the power n minus 1 derivative. So we introduce new variables x1, x2, etc., xn with this property. Okay, therefore what do you have? Now we can rewrite the equation as dxn by dt equal to f of t along with the new equations, namely dx1 by dt equal to x2 xn along with this particular equation. So what you have, you can write x as xn, then fn where you see that f1 is, yeah, please, yes. Yeah. Yeah, for the higher order equations. Yeah. In? Yeah, tell me. It is existing in what space? Yeah. Yeah. So, okay. Okay. Yeah. In the individual, yes. If the function is uniformly Lipschitz. Yeah, exactly, exactly. Yeah. Can you just wait for 5 minutes, because I will be dealing with that problem there. Okay, right. So you have f of xt is f1, f2, etc. fn, where f1 of is equal to, what is f1? f1 is given by x2, etc. fn minus 1 of t is given by xn, and fn of xt is given by f of x1, x2, etc. xn. So these are the functions that you have. This f1 depends only on x2, fn minus 1 depends on xn, and fn xt is the given f of x1, x2, etc. Now you see that you can now transform the whole equation into the system. It's a first order system for n unknowns, and you see that by our design the first component of x is going to give you the solution. Okay, you can solve this problem. And how do the initial conditions look like? Exactly like this, something like x t naught equal to x naught. What does that mean? x1 t naught is equal to some number, x2 t naught equal to some number, etc. So once the initial value problem for this An initial value problem for this equation will be dxn by dt, sorry, dx, okay, x nth derivative equal to f of x1 derivative x n minus 1 derivative t. With the initial condition, there will be n conditions coming there. X t naught equal to x 1 naught, say, x derivative t naught equal to etc. x kth derivative at t naught equal to, what is it? It is going to be x k plus 1 0. I will write here. By your notation, etc. And you have up to x n minus 1 derivative at t naught. So you have a point x1 naught, x2 naught, etc. So x naught is equal to that is the initial point. So you see that you have completely transformed this into a system of this kind. And then you see that the initial conditions, this is the initial value problem for an nth order equation with these set of conditions. And this takes the form this is the system that emerges. What is the relation between the solution of that and the solution of this? You see that the first component by design, what is it? x1 is equal to x. x1 is the first component of the solution, and the first component becomes the solution of the differential equation. Okay, so that is the relation between these two. So every nth order equation or even nth order systems can be transformed into first order systems, and from the solutions of the first order systems you can immediately write down the solution of the higher order system, and vice versa. So the general theory that we develop for the systems is equally well valid with the corresponding interpretations for the nth order equation or the higher order systems. That's the one remark. We will deal with nth order linear equations later, then things will be more clear. Anyway, there is nothing to be clear here. Okay. So let me start with the next thing, a special class of equations which are extremely important because you can develop a very nice theory for that. So take this system. Where f, this is equal to we assume the following. We take fi xt xj That means Fi xt is of the form sigma aijt xj bit. This is a very special class of equations called the linear equations. Okay, I will give an example. The example is this. These are all functions of t. So let me write here a11t dx2 by dt here aij's and bi's are all functions of t defined for some interval t1 less than t less than t2. This is what you call a linear system. Okay, and this linear system has some special properties. Now I will do a little bit of classification on that. I am going to assume that aij's are continuous on the interval t1 to t2. That is the basic assumption that I make. Okay, then you see that this gets transformed into it's in fact a system of equations, and all the theory that we have developed works here. But let us see where the solution is defined. Can you get any definite information about this? Let us explore this example. Okay, so you take x to be x1 x2 and you take y to be y2, that is xt and yt. Okay, then what is this one? So you have two. Okay. What is f of what is this? This is equal to a vector. You get a11t x1, and with these notations what you get? You get a11 x1 minus y1 plus a12 this bt cancels in both cases, b1t and b2t, and comma a21 now we estimate this. Take the norm of this. See, this is a vector now. I am taking the norm of this. Norm is the sense of the Euclidean norm. But what I can say is that, you see, this vector, okay, we can simplify the problem. We have already done the work for that. Suppose f of xt is Then we say that we have shown that f is Lipschitz in X if and only if each Fi this we have shown already. In the early part when we introduced the notation. Therefore, now you see that this is a vector valued function, this is a scalar valued function. So what you demand is that all the Fi's are Lipschitz in X. Okay. What does that mean here? If you take the components F1 and F2, what are the components of F here? So the component of this, see, this is your F1 and this is your F2. You want each one of these to be Lipschitz. So let me just investigate this. See, we have, what is that, Fi of BIT. That is your Fi. Now it is enough to show that each Fi is Lipschitz. Okay. Now I assume are continuous on T2. Okay, see, this may be a bounded interval or an unbounded interval, doesn't matter. Okay. Now suppose I assume this and let me take the interval t1 less than t1 prime . So I take this interval t1 prime, t2 prime, which is contained in now I am assuming the functions are continuous on the interval t1 t2, open interval t1 t2. Now what I want to show is that this is uniformly Lipschitz on any strip of the form. The strip is of the form okay. So let me do that. And I should not write this. Yeah, what I have is this, that is on cross Rn. Okay, so let me do that. How does that come? So what you have to do, you have to look at this Fi this you want to estimate with this a real number. This you know is less than or equal to, see, you take Aijt and Bit bounded on this interval t1 prime to t2. So let m. It is bounded because once it is continuous and this is a compact interval, therefore all these continuous functions are bounded. So you can take the common bound as m. If so, what do you get? You get this is less than or equal to modulus of this. So what do you get? You are taking the difference between the, so B8 is go away. So what you are left with is this m sorry, it is xj minus yj, j running from 1 to, this is what you get. And you can easily see that there is some constant k for which you compute the constant, for which this is less than or equal to norm of, this is the Rn R2 norm. So I will just, our notation was just putting bar but understanding it as the norm in Rn, okay, where k can be estimated because you see that each xi mod xi minus xj is less than or equal to norm of x minus y. Therefore it is actually m times n, that will be a possible k. Okay, so once m is fixed, you see that it, and the number n is known, then the k is fixed. Therefore you see that each fi is uniformly Lipschitz on the strip, what is it, T1, I wrote it down here, what is that, T1 so the uniform Lipschitz condition is satisfied here, okay, with respect to x. So our next step is that each fi satisfies is uniformly Lipschitz, therefore you see that capital F is uniformly Lipschitz. So you can from there conclude that capital F is uniformly Lipschitz. Now apply the theorem. If you apply the theorem, now it follows that every solution is defined for the initial value problem on the whole interval t1 prime to t2 prime. Weakness theorem. For the linear system, dx by assuming continuity of aijt and bt, every solution is defined on So we know that the maximal interval on which it is defined, now you see that it depends on what T1, T2 is. If it is minus infinity to plus infinity, then you see that every solution is defined on the entire interval minus infinity to plus infinity. Okay, right? So that is the interval on which the solutions for linear systems are defined. Okay. So we have shown that it is uniformly Lipschitz, therefore that particular result can be applied. So you don't have to worry too much about the interval on which the solution is defined once the general condition that Aij's and Bi's are continuous functions. Okay. Now let us start looking at this system more closely. So let me make some definitions. Homogeneous. We say that the system is a homogeneous system if Bit equal to 0 I. That means this part is not there. Sorry, yeah. Bit is identically equal to 0. Then the equation is x. Okay. The other, if some Bi is not equal to 0, then the system is a non-homogeneous linear system. So that's about homogeneous system and the non-homogeneous system. Now what advantage do we have when we are dealing with linear systems? The advantage that we have is that the entire power of linear algebra can be used. Okay, so linear algebra comes into play when we look at the class of equations of this system. So let us see how it enters the arena. So we start working with the homogeneous system. Okay. So what is the equation? The equation is this. Where Fi xt is j from 1 to n aij t is a function of t. It's that is Vt is equal to 0 for some t1 less than t. Now we assume that aij's are continuous. So we assume aij's are continuous functions for over the interval t1. Then we have already seen that the solutions are defined on the entire interval, open interval t1 to t2, because if you take any compact subinterval of that, it is defined on that compact interval for every compact subinterval of that. So therefore it is defined on the whole interval minus, t1 to t2, right. Now we make some observations. What is xt identically equal to 0? Xt identically equal to 0 is xt which is given by, that is x1t equal to 0, x2t equal to 0, etc. identically equal to 0. Now you see that, immediately see that xt identically equal to 0 is a solution of the homogeneous system. The next observation is this: if xt and yt are two solutions, of the system, then C1 or let me write alpha xt plus beta yt is a solution of the system. I think you should be able to prove this for alpha beta belonging to is a real number or real numbers. Therefore, if you look at the class of solutions So if you look at the class of solutions, namely, suppose I call this S, such that f of xt, where f has this linear structure. Assuming the continuity, etc., etc., linear space. It's a linear space of R. So you see you have the interval t1 to t2 on which you have now vector valued functions, continuous functions which turn out to be, or differentiable functions which turn out to be solutions of this equation. So we have what it demands is that xt should be, this class is xt differentiable. Xt differentiable means each component is a differentiable function. That's simple. Then this class of functions form what you call a vector space. Okay, so some nice structure is emerging. When you have a vector space, I'm not going into the structure of the vector space, etc., since you are already done enough of linear algebra to know what it is. We are talking about continuous vector valued functions on the interval t1 to t2. So it is from then this collection forms a vector space where the addition now is of course x plus y and these are vectors, you remember, these are vector valued functions. So it is well defined. Okay. So this is the linear space operation. So now the next question that you ask is, what could you say about the dimension of S? So S is contained in C1 it's a vector valued function. I am talking about vector valued function, not the usual. So this is okay. So you ask, what could you say about the dimension of? Now you see that at the outset we would expect this to be infinite dimensional. Why? Because if you take even this simple problem, continuous functions over the interval 0, 1 with the usual addition and scalar multiplication, it forms a vector space, and this is infinite dimensional. In fact, all polynomial functions are infinite dimensional. Okay. So at the outset you expect this to be infinite dimensional. But what we are going to, it's a beautiful theorem. What we are going to say is that the solution space of this system of linear equations, linear homogeneous equations, form a vector space of dimension n. Okay, be true is called the order of the system. Order of the system in the sense that the number of solutions what you call so it is n dimensional. So this is the n that comes. Okay. But this is a beautiful theorem. It's not infinite dimension, it is finite dimension. Okay, for ordinary differential equations, this is the story. Okay, what are the advantages? If you can prove this, then naturally you can have a basis for S consisting of exactly n solutions. Okay, and in terms of these n solutions, we can express every solution as a linear combination of them. Okay. Now if you just recall your elementary differential equations that you have done earlier, suppose you take a second order linear equation with constant coefficients. You would have been solving this. What would have been the method that you have adopted? If you take the homogeneous equation, then the method that you have adopted is the following. You write down the auxiliary equation, find if you get a polynomial of degree n, and then find the roots of that, write down solutions corresponding to each root of it, put them together, you get the general solution. This technique you would have been told, but now what we are doing is the theory which supports it. Okay. So let us prove this first of all. Okay. So we have to find how do we work on this? You find a basis for this solution. So we make the following observation. See, one of the powerful things in our theory is the following. That is, if you have an equation dx by dt equal to f xt, xt naught equal to x naught, then there exists a unique solution. That means the initial conditions fix the solution. Once the initial condition is given, the solution is fixed. That means just like saying the birth time fixes your life. Okay, in the astrology you have such a belief that the birth time actually fixes your future life. So that fixes the initial condition. So a similar statement you are making. Initially, if you fix what your solution is, then it is known for the entire interval. Therefore, see, what are the initial conditions? This x naught is a vector in Rn. Okay. Therefore, you see that now let us take this notation, that is E1 to be 1 0 0 etc. En to be This is the standard basis. Standard basis for Rn. Okay. Now what one does is this. See, you look at the equation. It's a linear equation, linear homogeneous. Homogeneous system. You take the initial condition x t dot n for I running from, so you have now n problems, each with a different initial condition. So what you ask is the following. You have now, corresponding to each I, you have a solution, you call that xit. xit here. This is for all I equal to now what I prove is this. These set of functions, so vector valued functions form a linearly independent set. Okay. Not only that, this collection basis for S. These are the two things that we prove. It is linearly independent, as well as every solution of this equation can be written as a linear combination of this. Okay, first of all, let us prove that this is a linearly independent set. What do we have to prove? We have to prove this. Suppose x and t. Okay. Then you observe that okay, let us just recall. What do we mean by k vector valued functions are linearly independent? Means what? If and only if equal to 0 implies zero. Okay, where of course yi. I am not assuming they are solutions or any such thing. All that I am saying is that some k functions are linearly independent. Now, if you just take the precondition for being a solution, namely that x has a continuous derivative, then you have a class of functions, C1 class of functions. Now, C1 class of functions is an infinite dimensional space. So, I am now defining what you mean by a linearly independent set. Okay, in that. It's like you take the simple case on the interval, say, see, when do you say ft and gt are linearly independent on zero to 1. One of them can be obtained as a scalar multiple of the other, or in other words, if you have a scalar multiple of these two functions vanishing for all t, then this has to be, the C1 has to be 0, C2 has to be 0. Then you say it is linearly independent. Okay, now let us work on that. So this is the definition of linear independence. Now we make an observation. Suppose or let me put general K are solutions of fxt on T2 and are linearly independent if for T0 the vectors And of course the converse is also true. Therefore I can write here if and only if. Okay, so this is what I want to prove. So let me assume, let me give the proof. Assume on T1. Okay, I will prove that they are linearly dependent Let us assume that they are linearly dependent on this. Then what do you have? Then there exists Ck, not all of them zero, such that C1 equal to 0. So not all these constants are simultaneously 0. So define for these constants so you take these set of constants and for that you define this. What can you say about xt? So we have dx by dt f of xt, because you see that dx by dt equal to c1 dx1 by dt plus etc. ck dxk by dt. Okay, and what more you have? You have x. Okay, what can you say about this solution? Is it identically equal to 0? Okay, so x t naught equal to 0, which implies xt is identically equal to 0. Why it is so? Because you know that if your initial data is a 0 condition, the initial condition is that it vanishes, then the whole solution vanishes. So xt is identically equal to 0. So you see that xt is a solution which is identically equal to 0, is an identically 0 solution of the differential equation. Okay, what does it mean? So what does it mean? It means that identically equal to 0, what does this mean? This implies are k solutions of the differential equation So initially at some point x1 t0, x2 t0, etc., xn t0 is linearly dependent, then the corresponding solutions x1t, x2t, etc., xn t is also linearly dependent. Okay. And suppose initially the initial data is a linearly independent set, then what you have? You have c1 x1, c2 x2 plus etc. c1 x1 t0 plus etc. ck xk t0 equal to 0 implies what? You get c1 equal to 0, c2 equal to 0, ck equal to 0 under the assumption that x1, x2, etc. xk are linearly independent vectors. Now these are linearly independent vectors. Now corresponding to each xi t, you have got each xi t0, you have got corresponding solutions xi t of the differential equation. Then what do you get? You see that suppose you take xt, c1 x1 t, c2 x2 t, etc., ck xk t. Okay. So xt is identically 0 if and only if sorry, I mean what I mean to say is this. Therefore, once you take an initial condition which is a set of linearly independent vectors, then the corresponding solutions also form a linearly independent solution. And how many such vectors you can choose? You can choose at most n. In fact, you can choose specifically e1, e2, etc., en. They form a linearly independent set. You have the corresponding solutions for each one of these ei's, and those functions also form a linearly independent set of solutions, or the solution space will be spanned by these set of functions. Okay, so write down, you give an explicit, write down the proof of this theorem. Okay, so that gives you that the dimension of S is equal to n. Now let me make some remarks. Let us consider the one-dimensional problem. It will give you some insight. Suppose you take the interval 0 to 1. Suppose you take two functions. So for each point t0, you see, you can fix up constants, non-zero constants, such that, suppose I call this f and g. Equal to 0. That is easy because these are just scalars, so you can work them out. But that does not mean that the two functions are linearly dependent, because you see that these scalars would really depend on the point. For each point it is going to be a different set of constant that comes. Okay. On the other hand, suppose you put the restriction that both f and g are solutions of an equation, if you put the restriction that these two functions are solutions of the differential equation, then what it says is that if at some point t0, f t0 is equal to c times g t0, I am assuming both f and g are solutions of this equation. I mean, this is linear, so I am writing this as, okay, I am assuming this is a linear equation, a linear homogeneous equation, and suppose I take two functions which are solutions of that, then you see that this is going to be, if they are linearly dependent at one point, then it is linearly independent everywhere. Okay, I'll elaborate on this with more specific examples chosen. So essentially the solutions are linearly independent if and only if their values at some point is linearly independent, and therefore at every point it is linearly independent. This is the problem. And this is an if and only if condition. Therefore the dimension of S is equal to n. Therefore it is enough to find functions possibly like this: dx by dt I'll introduce a new notation. See, what about these functions? Suppose I have f of xt fn, and this is equal to, with fi xj, then I can rewrite this column vector as a ax, where A is given by the matrix aijt acting over x. So you can see that aijt, if you take the matrix then I write this as where A is equal to the n by n matrix and then let me write this as AT. Then ATX these are the vectors. Okay. So all that I want to do is the following. I take this system of equation and solve this with EI. Then you see that even E2 etc. En are linearly independent vectors, therefore the corresponding solution is a linearly independent solution. Oh, sorry. I think I have exceeded the time. Sorry for that. Thank you. I think I will stop here. I think I will continue with this next class. Fine. Only if not everybody is